So a quick revision video on atomic structure, radioactivity, radiations, alpha radiations, nuclear equations. Let's just get started. So atomic structure. Now what you need to know for your GCSE exams is that this is a model of an atom. This part is a nucleus. Sorry about that. Nucleus. And what does nucleus consist of? It consists of protons and neutrons. So most of the mass of the atom is at the center. That's why in the Rutherford's experiment, very few alpha particles were deflected back. That shows that the mass is very small and at the center. Then most of them went straight through. That shows that the atom is empty. Okay, well, you can see that most of the atom is empty, and very few were deflected by a few were deflected by a small angle. That shows that the nucleus is positive. And why is the nucleus positive? Because it has protons inside it. Now the nucleus have protons and neutrons. Atom is empty. The electrons are in the outer shells. You need to know that the relative charge of electron with respect to proton is -1. The charge of proton is +1, and the neutron has no charge. The charge of neutron is 0. When this outer electron is removed, that process is called ionization. And because alpha particles are heavy, they are very good at ionization. They have the highest ionizing capacity. Say this is alpha particle has the highest ionizing capacity because they're the heaviest of all the 3 radiations. Now the ionization, if an electron is removed, it forms a positive ion, and if it ends up gaining an electron, if electron goes inside, it forms a negative ion. Okay. So now about the atom, you need to know all of these. So again, pause and read through it, most of it. And then the next thing what we need to know as a GCSE student is this notation. So this is notation for a uranium atom. This one shows the mass number, which is the sum of protons and neutrons. This one shows the atomic number, which is the number of protons. Now, if the atom is neutral, it's not an ion, then electrons and protons are both equal, and in this case, they are both 92. To get the number of neutrons, you subtract 235 and 92, and you get 143. That is the number of neutrons. Now, you need to know the definition of isotopes. Okay, what are they? They are atoms of same element. As you can see, they're all carbon. So they're atoms of same element. Same number of protons. So as you can see, 6 protons, 6 protons, 6 protons, but different number of neutrons, 6, 7, and 8. Yeah, 6, 7. Okay. Same chemical properties, different mass. So why do they have same chemical properties? Because they have same number of electrons. Remember, protons and electrons are same in number if the atom is neutral. Electron decides what will be the chemical properties. Because they all have same number of electrons, they have same chemical properties. And they have different mass because the number of neutrons are different. Some of the isotopes are unstable, like this carbon-14 here. It's a radioactive isotope. Because why is it radioactive? Because it emits alpha, beta, or gamma radiations. Okay. Again, pause and read through the information. The next one is the models of atoms. So over the period of time, different models were discovered, but what you need to be very good at is the plum pudding model and the Rutherford's model, which is also called a nuclear model. So the plum pudding model is like a ball of positive charge. So the entire ball is made up of positive charge, and what you have as electrons is they are embedded in it. So electrons are like these raisins in your pudding. So the green part is the electrons and the red part is entire positive. But this model was proven wrong by the Rutherford alpha particle scattering experiment, and then this is what his model looked like. So according to his model, the positive was at the center. Now why he came up with that was because very few alpha particles bounce back, so showing that the center should be positive and very small, and most of the alpha particle went straight, which showed that the entire space should be, most of the space inside the atom should be empty. Now next is the radioactive radiations. Now what happens is every atom is supposed to be stable. Now what you need to know is that there are some unstable nuclei, and nuclei is made up of protons and neutrons. So some nuclei in the periodic table are unstable and they become stable. So right now, let's say whatever screen you're watching, that is a stable screen. If that was an unstable screen, it would spontaneously and randomly start emitting radiations till it becomes stable. So such process is called radioactivity. So when an unstable nuclei becomes a stable nuclei by emitting three kinds of radiation, alpha, beta, and gamma, that process is called radioactivity. And radioactivity is a very random process and it's spontaneous as in it doesn't need any energy from outside to happen. Even if you heat a radioactive substance, so if it is a red dot that you can see on your screen is a radioactive substance, you heat it, nothing would still happen. You cannot increase or decrease the radioactivity by heating it or by freezing it. That means spontaneity. So it is a spontaneous, that means it happens on its own. And random, that means if you have hundreds or thousands of radioactive nucleus, you cannot tell which one of these would decay and would become stable. Let's say this is 9. Let's just take one more. So these 10 unstable nucleus become 5 after, let's say, 2 hours. So we can't tell which of the 5 will remain after 2 hours. That's why this is random. And this 2 hour would then be called as half-life, because the 10 radioactive nuclei has now become 5. So that is called half-life. Now you need to know the properties of alpha, beta, gamma, and sometimes neutron too. The charge, you need to know the charge is +2, the charge in beta is -1, gamma has no charge. The mass of alpha is, or another symbol for alpha is 2He4, so you can see the mass number is 4. This is, beta is nothing but an electron, so -1E0. We know that the approximate mass of electron is 0, so that's why it's 0. Gamma has no charge, no mass, because it is an electromagnetic wave. Go ahead, pause and read it. And also then you need to know, sometimes your exam would give you a graph. Okay, so a graph, this one shows a radioactive decay. It's an exponential graph. Say, let's say it started with the activity. So this is activity. It started with an activity of let's say 500 becquerels. Okay, so that's the unit of activity. Radioactive substances decay. How many atoms are decaying every second? That is measured in becquerels. So it starts with an activity of 500 and it becomes 250 in, let's say, 0 and 4 hours. So then it'll become 125 in next 4 hours. So this will be 8 hours and so on. So this is time in hours. So this is then used to calculate or find out the half-life. So the half-life of this particular radioactive substance is 4 hours, because that is the time in which 500 becquerels became 250 becquerels. Now, whenever certain radiations are emitted, like in this case, an alpha particle is emitted, and in this case, a beta particle is emitted. So whenever certain radiations are emitted, the atomic number and the mass number might change. So you need to balance both the sides. And how do you balance both the sides? It's just, see on the top of it here, I have 234 here and I have 4 here. So 234 plus 4 is 238, and here is also 238. Now you need to know that the mass number of alpha is 4. So sometimes it'll just say it gives out a alpha particle. So you need to figure out this mass number then. Okay, and then this atomic number should also be balanced. As you can see, 90 plus 2 is 92 on this side and 92 on this side. For a beta particle, C7 minus 1 is 6, and this side is also 6. 14 and 14 plus 0 is also 14. So you balance the atomic number and the mass number on both the sides. Another slide just to give you a meaning of half-life again. Say if it starts with 1, starts at 800 becquerel, after one half-life it would become 400. Sometimes the question asks you in percentage, 50% would remain. Sometimes the questions ask you in terms of fraction, half of it remain. So after 2 half-lives, it will become 1/4 or 25%. You can go ahead, pause and read through it. Now this one, sometimes the question would be just asking you the difference between contamination and irradiation. Say if somebody touches a radioactive substance, that is contamination. Fruits and vegetables are always irradiated to kill the bacteria which spoil them. Say that is irradiation. So let's say you're shining some gamma radiation on a piece of fruit. So because you're shining gamma radiations on it, there's no contact between the fruit and radioactive substance. So when there is no contact and only the radiations are hitting it, it is called irradiation. And when there is a contact between a radioactive substance and somebody, then it is contamination. Okay, and the most dangerous contaminant would be alpha particle, because alpha particle has the highest ionizing power. So sometimes if a cancer patient is irradiated with gamma radiation, he or she is not contaminated. They're just irradiated with gamma radiation to cure or to damage the cancer cells. And contamination would be when a patient would drink a radioactive tracer to diagnose a thyroid condition. So contamination, the radioactive substance would somehow get inside the body, and irradiation, you're just throwing some radiations on the surface. Okay, go ahead, pause and try to do these questions yourselves. And once you've done, mark the answers. Now the next one is the background radiations. Now background radiations is always present. Say what are they? They're coming from different kinds of rocks on Earth. They are emitting those radiations, but certain man-made sources like nuclear weapons, nuclear power plants, they're also the source of background radiations. Okay, now the uses of nuclear radiation, go ahead and pause and read through it. You need to remember one or two. Now nuclear fission and fusion, this is only for higher and single science students. Now fission is when a nucleus splits. So a bigger nucleus like 235, when it's bombarded with a neutron, it would break into 2 daughter nuclei. So daughter nuclei is a bigger nuclei breaking up into the smaller ones. The smaller ones are called daughter nuclei. But this fusion, the fission in which the bigger one breaks, it ends up producing radioactive waste. The fusion, on the other hand, something that happens inside our sun, is when two smaller nuclei like hydrogen combine to form helium. So hydrogen and hydrogen combines to form an helium. So this is fusion. So smaller ones combine to form bigger one. But this one is little safer, produces less radioactive waste, but we cannot do this easily. This requires a huge amount of energy to be done in the lab. So this is the reason why our sun has that much of energy. So this reaction is going on inside the sun day after day, that gives us so much heat, light, and different forms of energy. Now, this the cause of nuclear fission is a neutron hitting a heavy unstable nucleus. This one requires a higher temperature because these two nuclei, they are made up of protons, and if you want two protons to combine, they are positively charged. They're going to get they are going to repel each other. So you have to overcome this repulsion, and then you combine them into a bigger one, two protons. So this process, when you combine the two protons, it releases huge amount of energy to power our sun. But because they have to overcome this electrostatic repulsion, it is difficult to execute easily. Now, that's about it. So go through the video again, go through the first part, go through the radiations, pause and do it, and well done for learning and well done for watching.